This is Jack Jackson. In this video, we're going to start a series of videos deriving confidence intervals. And this will be broken up into a series of different videos here. This one is basically this first one on normal probability review and sampling distribution review. So before we continue developing, or actually start to develop, the concept of confidence intervals, we need to review some of our earlier work. Particularly, we need to be able to understand and use normal probability distributions. So we're going to review some of their properties and how to do some computations of probabilities and inverse probabilities there. And then also sampling distributions. You may see that I have homework problems here with some of these videos, and these are for my class, at least as of the time I'm making this out, these are the homework problems. Of course, this may be subject to change as the semesters go along. So first of all, remember that the probability density function of a normal distribution, the PDF, is a bell-shaped curve which is symmetric about its mean. Now, changing the mean, mu, shifts the graph horizontally, which of course that changes the center. And you can see here that the mu is the mean, it's also the median and the mode. And here we have several different normal distributions. All of them have a standard deviation of 1. And so you can see the effect of changing the mean, which changes the center, is just a horizontal shift. So this one right here, this blue one on the left, has a mean of -3, and then here's one with a mean of -2, -1, 0, 1, 2, and 3. The red one here in the middle with mean 0 is the standard normal distribution. Changing sigma alters the shape a little bit more. It alters the spread. So a lower standard deviation means less spread, more area near the mean. So the probability density is concentrated near the mean. Now remember, the total area is the total probability, so the area between the curve and the x-axis is always 1. So that makes it, with the smaller deviation, also is a little bit higher near at the mean. Okay, so the one with the smallest standard deviation is this tallest, skinniest one. This one has a standard deviation of 1/2. All of these have a mean of 0, so they're all centered up at 0. Here's the standard normal in red, has a mean of 0 and standard deviation of 1. Standard deviation of 2 is more spread out here. Standard deviation 3 even more spread out, and so forth. Now, given any normally distributed random variable x with mean, say, mu and standard deviation sigma, we can compute the probability that x is between a and b by computing areas between the graph of its PDF and the x-axis over the interval a to b. Luckily, we have shortcuts for this built into things like calculators. For example, on a TI-84, that's given by the command normal CDF a, b, mu, sigma, where you put in the appropriate numbers there for these 4 parameters. Now, it also turns out if we compute z-scores for the x values on both ends by taking an x value minus mu divided by sigma to get a z-score, then we can use a standard normal distribution or a z-distribution. A standard normal is a distribution with means 0 and standard deviation 1. Since it is a distribution of z-scores, sometimes I'll call that a z-distribution. And so a standard normal distribution is a distribution of z-scores. And probabilities from a general normal curve are the same as the probabilities between the corresponding z-scores from the standard normal curve. So in other words, what that means is if I want to find the probability from A to B, in other words, the probability that the original x is between A and B, on our calculator that would be normal CDF from A to B, mean mu, standard deviation sigma. That turns out to be the same as the probability of the z-score for A is less than z, which is less than the z-score for b. So in other words, a minus mu over sigma is less than z, which is less than b minus mu over sigma. And we find this probability from a standard normal. So we do normal CDF of a minus mu over sigma, comma, b minus mu over sigma, comma, 0, 1. If we know it's a standard normal, we can leave off the 0, 1 on a TI calculator and just write it like this last one here. Graphically, it looks like this. Now notice the scale is completely different here. So here this is 5. 5 would be off the screen here. This goes up to 0.4. This only goes up to about 0.2. So the scale is definitely different on these. But if you zoom in correctly, the right amount, you'll see that the graphs look exactly the same. The one on the top is the normal distribution with mean 5 and standard deviation 2, for example, and we want to find the probability between 3 and 9. So if you do distributions, which is, I think, second variables on the TI-84, it'll come up with this thing here, and you select normal CDF, which I think is the second one, and then it'll ask you for lower, which is 3, upper, which is 9, standard mean, which is mu, which is 5, standard deviation, which was 2, and then hit paste, and it'll put it in your calculator like this. Some of you may not have this little wizard thing. You just have to put it in directly. So, but anyway, it's normal CDF 3, 9, 5, 2, and you get that probability, which is the same as this red shaded area there. I got the graph out of a program called Minitab, and it comes up to be 0.819, which is this rounded off to 3 decimal places. You can get exactly the same probability in a corresponding area here by doing 3 minus 5 divided by 2. That's the x at the lower end minus the mean divided by the standard deviation to be -1 for the z-score that goes with 3. So that's right here, the z-score. Do the z-score at the top, which is 9 minus 5 divided by 2. That's C4 divided by 2. That's 2, and that's the z-score here at the top. And then do normal CDF from -1 to 2 with the mean of 0 and standard deviation 1, and notice you get exactly the same value. So probably it's easier just to do it this first way to actually compute the probability, but notice that it is equivalent either way. So once again, the properties of a standard normal distribution, let's take a look at those. It's bell-shaped curve, symmetric about the mean of 0, and it's symmetric about the y-axis. So the skewness is 0 because it's perfectly symmetric. The probability that x is less than 0 is 1/2. The probability that x is greater than 0 is 1/2. Mu is the mean, but that's also the median and the mode, and that's all 0. And the sigma is the standard deviation, which is 1. And here you see the graph, which is we call that a bell-shaped curve. Now, remember we compute probabilities using a TI-84, for example, like this. Use normal PDF to get the graph of the bell-shaped PDF curve, but we don't really need the PDF curve to find the probabilities. We really need the CDF. So we're going to use the normal CDF to compute probabilities. So for example, normal CDF A, B, mean, standard deviation in that order gives us the probability that x is between A and B from a normal distribution with whatever you put in for mean, and its standard deviation here for there. So normal CDF AB without the mean and standard deviation means it assumes a mean of 0 and 1 for standard deviation, so that's a normal standard normal, or Z distribution. So for example, if we want to compute the probability that x is between 3 and 9 for a normal distribution with mean 4 and standard deviation 2, we just put in normal CDF 3, 9, 4, 2, and hit enter, and boom, it gives us the answer very quickly. Now, if we're going to go backwards from that and do an inverse probability, so for example, let x be a normal distribution with a mean 8 and standard deviation 2, then we can solve problems of this form. Given x is less than p, and we want that probability, and we know that that probability is 0.75. So we know the probability, we want to find basically the percentile p. So this is basically finding the 75th percentile. Notice the value that's given here on the right is a probability to the left of p. So it's a left probability, a cumulative probability to the left. And the way this works is on the calculator, it's inverse norm, give it the probability to the left, then the mean and standard deviation. So notice when you hit distribution, you get this here, and here's exactly where we got normal PDF, normal CDF, and inverse norm, and some other things. Here we choose inverse norm. We give it 0.75, the 8, the 2, and it gives us the x value. So the probability that x is less than 9.34, etc., is exactly 0.75. All right. So let's have you do some practice here with this. So using a TI-84 or similar technology, this might be Excel or it might be some other graphing calculator, or some statistical program. Anyway, we're going to use technology here. We're not going to use tables in my class, so we're going to do everything from technology. So using a TI-84 or similar technology to compute the following probabilities or inverse probabilities, depending on which one's given. For a random variable x that has a normal distribution, and the mean of this one is 35 and standard deviation is 3. And please show all the digits produced by your calculator. And you can see these 5 problems here. So I'm going to ask you to do is to pause the video, get your calculator or technology out, work out these problems, write your answers down, and when you're done, come back and check your answers with my solutions on the next slide. Press pause now. Okay, so we have to do these problems. Here are the solutions, and you can see the calculator screens below. We want the probability that x is between 30 and 32. That's just normal CDF. 30, 32, mean was 35, standard deviation, which is 2. Close parentheses, enter, and you get 0.06059755489. Probability that x is less than 30, well, we need normal CDF from negative infinity to 30. And if you remember from my earlier work, there's practically nothing, theoretically not nothing, but practically nothing, to the left of 10 standard deviations below the mean. So you can effectively use mean minus 10 times the standard deviation as negative infinity in these. Of course, it's not negative infinity, but and there definitely is some probability to the left of that, but it's so low that it happens that it would only affect digits that are beyond the ones that are shown here. So you use normal CDF of mean minus 10 times the standard deviation, that's 35 minus 10 times 3, comma, the upper limit of 30, comma, mean 35, comma, standard deviation 2, and close parentheses and enter, and we get there 0.0062, so forth. If you want to go to the right, then we want to go from 38 to infinity. So we use mean plus 10 times the standard deviation for infinity, and in place of infinity, and that works. So normal CDF of 38, 35 plus 10 times 3, again 35, 2 at the end, and there's our probability. Now the last 2 problems are inverse norm problems, inverse probability. So this one is the type where they give us the probability to the left. That's set up exactly how an inverse norm works. So we put this 0.05 as the first number entered, the probability to the left, and of course we give it mean and standard deviation, and it gives us an x value of 30.065, etc. So about 30.065, the probability that we're to the left of that is 0.05. Now the next one gives us a probability to the right, not to the left. So we need to find the corresponding probability to the left. Of course, it's just 1 minus 0.01, which is 0.99. So you do an inverse norm of 0.99, 35, 3. Again, that's the last numbers of the mean and standard deviation, and that gives you your answer there. Okay, now again, use calculator technology or something similar for this. Now, in this next one, we're going to look at a sampling distribution and do some computation exercises here. So suppose that we have a random variable x with a normal distribution, and that the distribution of x values has mean 35 and standard deviation 3, like in the last example. And now suppose we take a sample of size 9 from this distribution and record the sample mean, x bar, for this sample. Okay? Now, if we were to repeat this process over and over again, then the distribution of sample means would have its own distribution. Now, I've got a few questions here for you. First, what type of distribution is the distribution of sample means? 2, what is the mean of this distribution of sample means? 3, what is the standard deviation of the distribution of sample means? And then I have some probability questions, not about x, but about x bar. So once again, I would like you to pause the video, work through these problems on your own, and then come back and check them against the solutions here in the next slide. Press pause now. Well, the first thing that we know is the distribution of sample means is normal, because if the distribution of individual values is normal, if it's exactly normal, then the distribution of sample means is also exactly normal. We also get, that didn't apply in this case, but if we have a large sample size greater than 30, even if the distribution of individuals is not normal, then the distribution of sample means is at least approximately normal because of the central limit theorem. And then number 2, what is the mean of the distribution of sample means? Well, it turns out to be the same as the mean of the distribution of individuals. So the mean of the x bars is the same as the mean of the x's, which is 35 here. And what is the standard deviation of the distribution of sample means? The standard deviation of the distribution of sample means is the standard deviation of the distribution of individuals divided by the square root of the sample size, or in a formula, sigma of x bar equals sigma of x divided by square root of n. Now sigma of x's was 3, n was 9, square root of 9 is 3, 3 divided by 3 is 1, so the sigma of the x bars is 1, and here you have the two distributions graphed together. The black is the distribution of individuals, which is more variable, and then the distribution of sample means is the red graph, which has a smaller standard deviation, but has the same center. Now, to do the calculations here, what I did this time is I took the 35 and stored it as m, which was the mean, and then I computed the s, which was the 3 divided by square root of n, and which was just 1, and stored that as s. Now, anytime I need the mean or the standard deviation, I'll just refer to those as m and s in the calculator. So to do the first one, I need a probability here. So I want to go from, it's a normal, so I do normal CDF. I want to go from 30 to 32, that's lower to upper, and the mean of m and the standard deviation of s, and paste that in, and you can see there that probability is 0.0013496801. And then if I did the probability that x bar is less than 30, again I can use m minus 10s for negative infinity, and then go from 30, that's the negative infinity, then go up to 30, and then do m and s for a mean and standard deviation. We get this. Remember, this is scientific notation, so this means times 10 to the negative 7. So that's 0.6 zeros, and then a 2, 8, and 7, 105. So hopefully I got 6 zeros here. 1, 2, 3. Yeah, 3, 6. 6 after the decimal place. So good. 7 with the 1 in front. Probability of x bar being greater than 38. Okay, then we go from 38 to infinity. So in place of infinity, I use m plus 10s, and then m and s there, and so we get that probability. This is a probability to the left is 0.05, so that we put that in. Then we do an inverse norm with that m and s, and we get that value there. And then the last one, the probability that x is greater than c is 0.01, means the probability that x is less than c is 0.99. So we do inverse norm of 0.99 ms, and we get that, 37.3 something. These type of calculations here are exactly the kinds of calculations that we're going to be needing in working with confidence intervals. Okay, so we'll go on and continue this in the next video when we actually introduce confidence intervals and how to compute them.